Okay, I think the video is recorded. So for the midterm, you might have already went through the course schedule. We will have the first midterm in I think on Monday, October 18th at the tutorial time, which is 12:30 to 2:30. So there will be 2-hour sessions. And for the materials covered by the first midterm, it will be all the notes from the first one, note 1, to the note covered by the lecture today. So we will go through the fundamental concepts about the surveying, the basic measurements about the distance, and also the leveling. And that will be all the materials will be covered in the first midterm. We will have the I'm always available on emails or on Teams, so you can ask me any questions about the midterm, even during the reading week. Also, if you have any questions, you can contact the TA for any questions related to your homework, to the lab report, or to the midterm exam. This is a very brief introduction about the midterm, and tomorrow I will have more introductions about what we're going to include in the midterm one. Do you have any questions about midterm? Okay. If no, then there will be another thing about the deadlines of the lab reports. I noticed that you received several requests about the extension of the lab report, and it's for the lab report 2 and report 2 and 3. They are all due on Sunday next week, which would be October 17th. After reviewing the request, I understand that there will be some of you may have some business in this week to take in the exams of the other classes. Yes, that will be fine. With that, I can try to extend the deadline for the lab report 3, and it will be extended to the Sunday after the reading week. So that will be October 24th. I will make an announcement on Avenue to Learn to explain the details about the extension so that you won't miss it. Okay. If you have any questions, of course, just feel free to let me know, and I will definitely try my best to accommodate your schedule and also try to give you more clear answers about the midterm exams. And I see the questions about the format of the midterm. The midterm will be placed. It will be held online, and we will deliver all the exam sheets on Avenue to Learn just before the midterm exam, and you will download that one and work on it. We will not do any proctor format for the midterm exam, so you just work on the exam and upload the answer sheet to the Dropbox in Avenue. And the duration of the exam is about 2 hours. You don't need to work on 2 hours. It just take around 1 hour or a little bit longer to finish the exam. And there we have the extended time for you to upload all the answer sheet. So this is the reason I want to reserve in 2 hours so that everyone can have enough time. And the exam is open book, open notes, so you can bring any notes with you for the during the exam. And at most of the time, you just need to follow the materials from the notes. And of course, the homework assignment is very important. The questions in the midterm exam will be very similar to the homework assignment and the examples in the notes. So I would encourage you to go through all the examples and the homework questions. You also have already received the solutions for all the homework questions, homework 1 and homework 2. So review them. It will be very helpful for you to go through the first midterm. Okay. Any additional questions? If no, then I will start the lecture today. Try to finish the topic about the leveling, and also depending on whether we have time, we will go to check the next lecture about the angles and directions. Okay. This one. So last week we have went through the introduction about the leveling, the basic method for you to measure the vertical distance, and we introduced the direct leveling method where you can just use the transit level to measure the elevation difference between 2 points directly. And we can then combine multiple direct leveling together. With that, we can then measure the elevation difference between 2 points which are really far away to each other. I guess I forgot to share my screen. Sorry. Okay. Can you see my screen now? Okay. Hope it's already shared. So for the method, actually the method you applied in your lab 2 experiment is called the differential leveling. With that one, we can estimate the elevation difference of multiple points or about 2 points which are really far away to each other. In the differential leveling, there are some concepts we have to know, including the benchmarks, which would be the 1 point where we know the elevation, the true elevation of this point. And we also can have some temporary benchmarks where they can be applied as the temporary points between during the experiment. With that, you can do some corrections about the potential errors you conducted during the experiment. And there are some turning points where you, if the 2 measured distance is really far away, then you need to specify a turning point in between so that you can you are able to observe both of them, and you can set up multiple turning points between the 2 target locations and measure the elevation gradually to reach the target. And you also have the foresight and the backside. The foresight represents the observation to the next point where you place the which will be the next turning point, and the backside will be the observation back to the previous turning point or to the benchmark. Also, you will have some intermediate site where it's usually applied for the profile leveling, and we're going to show you the details about how to conduct the profile leveling with multiple observation with multiple points, so that I can get the elevations quickly with a smaller number of the turning points. Okay, and this figure shows the progress for you to conduct the differential leveling. Well, you will see that you will need to conduct the, for example, if we want to measure the elevation difference between 2 points, benchmark 1 and benchmark 2, and these two are really far away to each other. And for benchmark 2, it's even on the other side over here, so you cannot see well. Well, you cannot see where the next point it is from the benchmark 1. then you need to rely on several turning points. Here in this example, we just set 2 turning points. And with that, you are able to observe the set an instrument. First, set an instrument between benchmark 1 and turning point 1, and you will have the backside and foresight. Here, the backside will represent the observation back to the benchmark 1. So we said this one is the backside, and the foresight will be the observation you were trying to read to the turning point 1. So with these two readings, you can then identify the elevation difference between benchmark 1 and turning point 1. I mean, in the next page, I'm going to show you how to do the calculation. And once you finish the measurement for the turning point 1, you can then move to the one location between turning point 1 and turning point 2. At this step, you will try to identify the elevation difference between turning point 1 and turning point 2. Still, you will have the backside to the turning point 1 and the foresight to the turning point 2. And again, you can repeat this process for many times until you reach to the last segment, where you will have the instrument set between the turning point 2, or the last turning point is specified, and the benchmark 2. You can then measure the elevation difference between the turning point 2 and benchmark 2 based on the backside and the foresight. So with that, you are able to measure the elevation of all the turning points, and you can then estimate the turning point of benchmark 2 or any target point from the differential leveling. So that's the way for us to conduct the differential leveling for the to measure the vertical distance or the elevation difference. To do the experiment, to do the calculation, we will actually have some formulas for you to calculate the elevations of each turning point, and also eventually find out the elevation of the target point. So for the differential, usually you will be given with the elevation of 2 points, the benchmark 1 or the benchmark, and also the benchmark 2. We know their elevation, and then we have the read for each direct leveling in this differential leveling. So we have the readings. We have for the readings between benchmark 1 and the turning point 1, we have the backside 1 and the foresight 1, and that's the first direct leveling. And we also have the backside 2 and foresight 2. And if we have the other different direct leveling, you will have different backside and foresight readings. In the previous example, we will only have the third one, backside 3, and the foresight 3. And depending on how many observations you will have in the experiment, you will have multiple readings. And then for the elevation of the turning point 1, we can actually calculate the elevation of turning point 1 as the elevation of the benchmark 1 plus the backside 1 minus the foresight 1. So this is the elevation of the turning point 1. It is determined by the original elevation of the benchmark and the backside and the foresight, which would be 2 readings from the direct leveling. And similarly, you can calculate the elevation of turning point 2. With that, you need to use the elevation of the turning point 1 plus the backside 2 minus the foresight 2. And similarly, you can try to repeat this process to find out the elevation of the other turning points. In the previous example, you can calculate the estimated elevation of the benchmark 2 as the turning point 2 plus backside 3 minus foreside 3. So this is the estimated elevation. So it's not the true elevation, it's the elevation you actually estimated from your experiment. If we are provided with the benchmark 2, the elevation of the benchmark 2, you can actually find out the error of your measurement. Would be the difference between the estimated elevation and the true elevation. So we have in your experiment, you have always need to check the potential error. If the error is too large, it probably means that you have some wrong operations during the experiment, or you probably apply the wrong formulas to calculate the elevation of the turning points. So that's the way for you to conduct the differential leveling. And in this page, you will actually see how you need to record all the readings in the field. Basically, for this table will shows the recording for the examples in the previous page. So we have benchmark 1, the turning point 1, turning point 2, and benchmark 2. And also for each measurement, each direct leveling, we will have the backside and the foreside. Another thing you have to keep in your mind that if possible, it will be highly encouraging for you to measure the height of the instrument so that you will have some way to make a correction about your errors. Especially if you observe some errors, you can refer to the height of the instrument to find out the potential wrong adjustment in the experiment. So to do the recording, we will first put the backside 1 in this cell, and also record the height. The first height you applied for the first measurement, and then you put the foreside 1 in this cell, which is related in the same row of the turning point 1. And similarly, you can go to record the other readings. So you will have the backside 2, the height 2, and the foreside 2. And again, you will also have the backside 3, the height 3, and the foreside 3. And also we are provided with the elevation of benchmark 1, and also we know the elevation of the benchmark 2. This one is also given. So what we want to do is that we need to calculate the elevation of each point from the measurement. With that, we have the turning point 1 with the elevation of benchmark 1 plus backside 1 minus foreside 1. Similarly, have the turning point 2 as TP1 plus backside 2 minus foreside 2. And you have the estimated value for the benchmark 2 as TP2 plus BS3 minus FS3. And you always need to calculate the error. So you have to record the error as the estimated benchmark 2 minus the true benchmark. And in your lab recording, you also need to have some descriptions about the experiment, like how you conduct the experiment for each differential, for each direct leveling, and what's the how many turning points you actually applied, and did you do any adjustment about the tripod, or if there's anything wrong about your operation of the instrument, you have to record it in the description section. So that's the recording for the differential leveling. With that, you can we can find out the elevation of all the turning points and of course the estimated elevation of the benchmarks, and you know the errors in your experiment. If the error is too large, you may need to go back to check each measurement and find out where the error is. So this is the differential leveling, and in reality there will be actually several some other type of the differential leveling. The one that we introduced in the previous page is called the line leveling. So in the line leveling, we know the benchmark, the elevations of two benchmarks at the beginning and at the end. And we will try to find out the elevation of the turning points, turning point 1 and turning point 2, and then we will have the we can then find out the error at the benchmark 2. With that, we can know whether how good the measurement is for the whole experiment. And the this is called the line leveling. It will start from one benchmark and end it at another benchmark with no elevations. And the second one is called the loop leveling. So with the loop leveling, we only have one benchmark. And this one is usually applied for us to measure the elevation of multiple points in the area that we are interested to measure. So we will have, for example, we are provided with the elevation of one benchmark, which is benchmark 1. Then we can try to estimate the elevation of the other points, the turning point 1, turning point 2, turning point 3, and turning point 4. We can conduct the experiment through those lines and measure the elevation of each point and then return it back to benchmark 1. And by doing this experiment, you can also have one value, one estimated elevation for the benchmark 1. And you can try to find out the difference between the true value of the elevation and the estimated value, and that will be the error you have to consider to make sure that your measurement is right or wrong. And the last one is called the open leveling. So with that, you will also only have one known location, which would be benchmark 1, and then you will do the measurement from this point, and then you can use benchmark 1 to elevate the elevation, or to measure the elevation of turning point 1 and turning point 2, turning point 3, and some other points. So for this kind of measurement, it will be ended at the location you want to measure, and of course you don't know the elevation of all those turning points, TP1, TP2, or TP3. So in that sense, we cannot identify the error. So the error is unknown in this case. That's also the reason we call this as the open-end leveling. Even though we can find out the elevations of the points we are interested to measure, but we don't know the errors in this measurement. So those would be some typical differential leveling method applied in reality. And the other thing I want to introduce in this class is about the potential method for you to balance the errors in the differential leveling. This is called the balancing the backside and the forward distance. With this kind of method, you are able to remove the errors during the experiment, even though even when the transit level is not adjusted appropriately. So to do this kind of adjustment, we want to make sure that the foresight distance, the horizontal distance, is the same to the backside distance, which means that we will have the value of dBs will be the same to dFs. And if we have this setting, then we can eliminate the curvature and refraction errors, and also remove the instrumental errors. So the figure here actually shows one typical instrumental errors during the experiment. So assuming that you have a true horizontal line, which will be the solid line, but if you did not adjust the transit level very well, you will actually have a certain angle, a very small angle, which will make your line on the side a little bit different from the true horizontal line. In that sense, what you will observe for the backside and the foreside will be wrong, and the arrow in this case will be, for example, for the backside. The arrow in the backside would be the distance approximately equal to the distance of the backside times the sine alpha. And similarly, you can find out the errors for the foreside as the distance of foreside times sine alpha. And in this case, if you have the distance of backside equals to the distance of foreside, you can easily find out that the arrow of the backside is the same to the arrow of the foreside. And then based on the calculation, like if we know the horizontal, the elevation of A, you can actually find out if this one is no. You can then find out the elevation of point B, point C, as the EA plus backside minus foreside, and then the error from your observation can be eliminated because the backside equals to the true backside from the horizontal line. Say that the true backside plus the arrow. And similarly for the foreside, it will equals to the true foreside plus the foreside arrow. And if these two are the same, then you will find that this one will be EA plus the true backside minus the true foreside, which will be the true elevation difference between point A and point B, or point C. So that's the way for you to try to improve the accuracy of your leveling experiment by balancing the backside and the foreside distance. The last thing I want to introduce about leveling is called the profile leveling. This is one method which can help you to conduct or try to find out the elevation of multiple points efficiently. So the way for us to do the profile leveling is like we want to first specify a hub, which is also the benchmark with no elevation, and then we can try to set up the level transit at some points between two hubs, hub 1 and hub 2, and also we can specify some turning points if they are really far away to each other. With that, you can then try to measure the elevation of multiple points along a straight line, or along any curved lines through the each direct leveling. For example, for the if we want to start with the benchmark 0 or benchmark 10, and we also have the hub at the end, and we want to measure the elevation at almost 12 points along this in a straight line. What we can do is like we will first specify the turning point, which is not along this straight line. Instead, is at some location which you can easily observe between benchmark 0 and turning point 1 with the transit level. And with that, you will have the backside about the benchmark 10 and the foresight to the turning point 1. And then you will have some intermediate side to observe the points along the line you're trying to measure. So you have in the first direct leveling, you will have level point 1, 2, 3, 4, 5, 6, 7, 8. You will have 8 points observed. And if you have some other points you want to further measure, you can then move your instrument to another point and try to have the backside to turning point 1 and the foresight to the hub and get the intermediate side of another 4 points. So with that, you will have the both backside and foresight to the turning point 1 and the hub and the intermediate sides to the points along the line you are trying to measure. And if there are more points you want to measure, you can set up more turning points and try to measure the intermediate size from those turning points to the points in the line you are trying to estimate. And then we can calculate the elevation of all those points along the line we are trying to measure. So here would be the field note for you to conduct the profile leveling, and you have to record the backside and the foresight for benchmarks and the turning points. And also you need to record the height for each measurement. And again, you need to get the foresight for turning points and also the hubs. But for those points along the line you're trying to measure, you will observe the intermediate foresight. And this is the information you will need to apply to measure the elevation of those points. Say that the point 0, there will be point 0 plus 0, point 0 plus 0 might be 0.1, 0.5, something like that. And with that, you can, let's see how we can measure the elevation, or how we can estimate the elevation of those points along the line we want to measure. Let's take the example of the first point. For this point, we have the backside to the benchmark 30. So we have benchmark 30, and we know the backside. So we say that it's a backside 1. And we also know the intermediate foresight. Then we minus the intermediate foresight. In this case, we will have the value of 30. This would be the elevation of the benchmark 30 plus the backside, that is 3.478 minus the intermediate foresight. The intermediate foresight is 3.617. With that, you can find out the elevation of the first point in the line as 29.861. And so that's the first point. And for the second point, this one is also calculated as benchmark 30 plus backside 1 minus the intermediate foresight 2, so which will give you the value as 30 plus 3.478 minus the intermediate foresight as 5.141, which will give you the value as 28.337. So for all these points between BM30 and TP1, you're going to need to use the backside and also the intermediate foresight to calculate the elevation. But for the other points, for example, for and the random points between turning point 1 and turning point 2, then we have to use the backside to the turning point 1, elevation of turning point 1, and the intermediate foresight to get this elevation. So that is TP1 plus backside 1 minus, I'm guessing this time that will be 2, minus the intermediate foresight. Just say it's K. So we have the value as 33.285 plus 3.134 minus 1.738, which will give you the value as 34.681. So you can do the calculation about the elevation of all the intermediate points along the line we are trying to measure. And you can, if the line is too long, you need to set up more turning points. And with that, you have the elevation. So every point, and also you can check the errors for the if it's this is kind of the loop leveling. You can check the errors once you return back to the original benchmark. So with that, we will complete the profile leveling, and then you can actually draw the a line to show the elevations along the along all the points, elevation of all the points along the line you measured. So this is actually the points along the line, and the vertical axis shows the elevation you measured from the profile leveling, and you can know what the slope of the line looks like from the profile leveling easily. And with that, in this case, you actually only conduct, for this example, you only conduct 1, 2, 3. You actually only conduct 3 backsides to complete the measurement of more than 10 points along the target line. So it will be very efficient. So that will be all about the leveling. Do you have any questions? Any questions about the leveling? If no, then I will go to the next next lecture about the new measurement, about the angles and the directions. And if you have any questions, you can just raise your hand, or you can type it in the meeting chat. Okay. So here the another important is the measuring the directions of a line, or if we want to identify the one point from another point, you need to specify. You need to find out the relative distance to that one, which comes from the leveling, and you want to identify the elevations of that point, which comes from the I mean, if you want to measure distance, that will be the taping method. If you want to measure the elevation difference, that will be the leveling method. And you also need to identify where you want, which direction you want to go. That will comes to the measurement of the angle and direction. So the definition of the angle is quite intuitive. Basically, it's defined based on the angle is defined with two directional lines. For example, if we have a point O, A, O to A, and O to B, then the angle between the relative locations of point A and point B. And usually, the angle is measured with the units of degree, gradient, and radian. For the degree, we have already introduced previously. For one revolution, the degree is with a degree that will be 360 degrees. But for the gradient, it's different. The gradient defined one revolution as 40, and for the radian, is defined as 2 pi. For the unit of degree, we have 1 degree equal to 60 minutes and 1 minute equal to 60 seconds. So this is a very common unit for us to measure the angle. The gradient method is not quite gradient unit is not quite common, but the radian is also very common and is also applied a lot for the calculation of the sinusoidal and sinusoidal functions. And basically, 1 radian of pi in the radian unit pi, 1 pi represents 180 degrees, and we can use this relationship to convert degree to radian, and then calculate the value of the sinusoidal functions. So that's the basic definition of the angle. The definition is pretty simple, but if we go to see the lines on the Earth, the directions on the Earth, it will become very complicated. Usually in the for the Earth, we can consider this as the surface of the Earth can be considered spherical, and the easiest way for us is that we need to use some geocentric system to describe the points on the surface of the Earth or at some locations below the ground. Generally, there will be two systems for us to describe a point, any point in the 3D space. The first one is called the rectangular system. So for the 3D coordinates, we will use the x, y, and z values to represent any location in the 3D space. And the second one is called the polar system. So in this system, it will use the 3 variables, one distance with 2 angles, which is R will represent the distance from the direct distance from this origin of these coordinates to the point you want to measure, and alpha, beta. These two is applied to identify the directions of the point in the polar system. I believe you have learned both of them in some fundamental math classes, so I won't go through the details about these two systems. In this class, we can rely on both systems to identify the location of identify one location in the 3D space, or to determine the distance between any 2 points in the 3D space, or to measure the angles, horizontal angles, vertical angles of any 2 lines. So the one in the previous page is the geocentric system. You will consider the Earth, use the center of the Earth as the origin. But in reality, usually we only want to consider if we just want to measure in a small area, we would like to have a simpler coordination system, which we call that the local coordination system. And for that one, we will assume that the plane is a flat, does not have any curve. So we can then just use the simple local coordination system with the coordinates from x, y, and z axis to identify any locations on the any locations you want to measure, to identify in this space, in the 3D space. So in this class, we will, I think especially for the angle measurement, we will focus on the local coordination system, where we will just consider the Earth is in the flat, and we're going to use the rectangular coordination system to measure the coordinates of x, y, and z coordinates of one point, and then use these values to identify the directions of any lines. Let's go to check one simple example. Here we will consider a line from P to A, and also from P to O. O is the origin. And with that, we want to find out the horizontal. We want to find out what's the horizontal angle of AP, the horizontal angle from AP to O. To identify the horizontal angle, what we want to do is like we will first try to find out the projected point OP and projected point OA to the base to the plane, to the XY plane, which will be A prime for the point A and P prime for point P. And with that, you can then connect the points O to P and O to P prime and A to P prime. And then this angle is just called the horizontal angle of APO. And of course, you can go to the you can try to project them to the other planes. It's also fine. You will find out that the angle would be the same. So that would be the horizontal projected line. For example, if we want to find out the vertical angle from O to P, you will need to find out the projected line from O to P, and then the angle between O to P and O to P prime and O to P would be defined as the vertical angle. So in this case, it will refer to as beta. That would be the vertical angle. And basically for all those angles defined in the 3D space, if we want to find out the horizontal, you need to go to the horizontal plane. If we want to find out the angles in vertical angle, you need to project them to some vertical plane, or you can find out the projected line and get the angles between the projected line and the original line directly. So this would be the horizontal angle in the 3D plane for horizontal and vertical angle in 3D plane for one line. I guess I run out of all the time, so I will stop here, and in the next lecture, I will continue the introduction about this lecture, and also as you're going to work on the lab 4 and lab 5 after the reading week. So and the lab 4 requires some background information. So I plan to have half of the class, half of the lectures are introducing this lecture, and the rest will be the introduction about the background information for the lecture 4 in the next lecture. So I think that will be all about the lecture today. Do you have any questions? If no, then that will be all about the lecture today. And just keep in mind about the schedule of the midterm and also the deadline of the lab reports. If you don't have any questions, I will close the meeting today. And I really appreciate your attendance to this class. I think that'll be all. Thank you very much, and I will see you tomorrow.